Now we make the question much more complicated. The circuit topology is the same as that in exercise 1. This is a series connection of a voltage source, a capacitor, and a resistor. The difference is the voltage source is a periodic excitation instead of a constant one. We always suppose the initial value of the capacitor voltage is 0. In the first condition, we suppose capital T, half of the period, is very large. It's far greater than tau. What does that mean? Do you still remember the concept of time constant in lecture 49? The whole transient process is finished after 3 tau to 5 tau. If capital T is far greater than tau, it means that the transient process is finished during the period from 0 to capital T. Capital T to 2 capital T is a second transient process after the first transient process comes to steady state. Let's analyze the process from 0 to capital T with 3 elements method. Obviously, UC 0 plus equals 0. UC infinite equals 100 volts. And tau equals RC. So we can see UCT equals 100 plus 0 minus 100 multiply e to the power minus t over tau, or 100 multiply 1 minus e to the power minus t over tau. This is the waveform. After it enters steady state, let's analyze the process from capital T to 2 capital T. UC capital T plus equals 100 volts. And UC infinite equals 0. Because the excitation is 0 from capital T to 2 capital T. This is the equivalent circuit. The electric charge consumed in this direction. So the steady state value is 0. Tau equals RC. So UC equals 100 multiply e to the power minus t minus capital T over RC. This part, you shouldn't make a mistake. The time axis starts from 0, so this is written as t minus capital T. Similarly, this is the waveform. The process starts all over again. Well, let's do an experiment to verify this analysis. This is the experiment of RC dynamic circuit with pulse sequence excitations. This is the experiment circuit. The resistance is 10K and the capacitor is 0.1 mu. So the time constant is 1 milliseconds. The input is square signal produced by virtual signal source, and it's connected to the channel 1 of the virtual oscilloscope. The frequency is 100 Hz. So the period is 1 milliseconds. The output is the capacitor voltage. It's connected to the channel 2 of the virtual scope. This is a voltage waveform of input and output displayed in virtual oscilloscope. The yellow one is the input square signal, and the green one is the capacitor voltage. During the positive half circle, capacitor voltage increases from negative value gradually and increases to the positive peak of the square wave. Since the time constant is very small, during the negative half cycle, capacitor voltage is decreased from positive value gradually and decreased to the negative peak of the square wave. In the second condition, capital T is close to tau without any other changes. The transient process cannot be finished during 0 to capital T, which means the previous transient process may not be over before the next transient process starts. Before analyzing, let's do a simulation. In this simulation, the topology is the same as the circuit and need to be analyzed. It's a series connection of a voltage source, capacitor, and a resistor. We mark the detail value here. The resistance is 1K, capacitance is 10 mu, so the time constant equals RC equals 0.01 seconds. The voltage source is a pulse sequence. 10 volts frequency is 100 Hz, so the cycle is 0.01 seconds. Half cycle is this. So the capital T is close to tau. For the oscilloscope, the red line measures the square wave, and the blue line measures the capacitor voltage. Run the simulation. You see, from the 0 point, the capacitor is charged and discharged, charged, discharged, charged, and discharged. After several cycles, it enters a steady state. What's this steady state? Suppose this is a start point of steady state. From one value, the capacitor is charged to some other value for half cycle. After that, it's discharged to the same value as the start point. After another half cycle, similarly, it also can be seen as that it's discharged to some value during its first half cycle, and it's charged to the same value during the second half cycle. This is the simulation result. You can see during 0 to capital T, the capacitor voltage is increased from an undetermined value with a negative exponent. Because capital T is close to tau, it cannot increase to the steady state value. The circuit is switched at t equals to capital T. Suppose the value is U2. During capital T to 2 capital T, the circuit has no excitation, and it decays with a negative exponent. Once the circuit is into steady state, it increases from time 0 to U2 during 0 to capital T, and it must decrease from U2 to U1 during capital T to 2 capital T. If the condition is like this, we say the circuit is in a steady state. You should notice that this steady state here is a steady state in dynamic process. In other words, after every cycle, the start point and the end point are the same. Now let's analyze this question. Find the steady state voltage UCT. The cycle is divided into two parts. During 0 to capital T, UC0 plus equals U1. It's a start point value. More importantly, what's the steady state value of UC? Is it U2 or 100 volts? Please think about it.